Okay, so let's review what we've discussed so far with regards to the definite integral. So we defined the definite integral, which we use the notation integral from a to b, f of x dx, and it's equal to the area underneath the curve between a and b. So this is the graph of f of x, and the integral is the area of this shaded region. With the additional understanding that if there is area beneath the x-axis, like something like this, then this area down here would count as negative, whereas area above the x-axis counts as positive. So we saw in the last video that we could approximate these integrals with Riemann sums. So we had a left-hand sum, which was sum from k equals 0 up to n minus 1 f of xk delta x, and the right-hand sum was the sum from k equals 1 to n f of xk delta x. And we had that delta x is equal to b minus a divided by n. xk, let me actually write that down here, it'll be easier to stay on the screen. So xk equals a plus k delta x. So we have these two sums. If we want to get the exact value of the integral, we can take the limit as the number of rectangles n goes to infinity. So we went through sort of the abstract formulation of these Riemann sums in the last lecture. This time what I'd like to do is give some concrete examples of what these things look like and how we can construct them. So as an example, let's use a Riemann sum to estimate integral from 0 to 1 x squared dx with, let's say, 5 subintervals. So how do we do this? Well, first let's look at what things are in this expression. So the lower bound of the integral is a, so a equals 0. The upper bound is b, so b equals 1. F of x is equal to x squared in this case. If we want 5 subintervals, then our delta x is equal to 1 minus 0 divided by n, which is 5 in this case. So delta x is 1/5, and x sub k is equal to a plus k times delta x, which in our case is going to be equal to 0 plus k delta x, or k divided by 5. So we can write down what these points are. x0 is equal to 0, x1 is equal to 1/5, x2 is equal to 2/5, x3 is equal to 3/5, x4 is equal to 4/5, x5 is equal to 5/5 or 1. So we have our parabola here, and we're dividing up the region from 1 to 5 into 5 equally sized, or sorry, 0 to 1, into 5 equally sized pieces. And then we'll form some rectangles to estimate this integral. So if we want to use a right-hand sum, then we would use this formula up here. So we'd have sum k equals 1 to n f of xk delta x. xk was k divided by 5. F was x squared, so we have the sum. We can write that n is equal to 5, and we have the sum of k over 5 squared. This is the f of xk term. Plus, or no, not plus, times delta x. Delta x is equal to 1/5. So if we simplify this, we'll get the sum from 1 to 5, k squared divided by 125. So now we can write out what terms we have. So if I plug in k equals 1, I'd get 1 over 125. K equals 2 gives me 4 over 125. K equals 3 gives me 9 over 125. And so on, up to 25 over 125 when k is equal to 5. We add all these terms up, and it turns out that we get 55 divided by 125, which is equal to 0.44. Okay, what if we wanted to use the left-hand sum? Well, if you take a look at these two formulas, the only difference is in the range we're summing over. In the left-hand sum, we're going from 0 to n minus 1. In the right-hand sum, we're going from 1 to n. So that means that we're still going to get this k squared over 125 for the stuff inside the sum, but now we're summing from 0 up to 4 instead of from 1 to 5. And that means that we get these same 4 terms here, then we get an initial term when k is equal to 0, but then this is just 0. So basically, we just get these terms that we had before without the 25 over 125. And that gives us 30 over 125, which is 0.24. And so we can see that the left-hand sum gave a lower value. This is to be expected because the function is increasing. That means the left-hand sum will give an underestimate of the true value. The right-hand sum will give an overestimate of the true value of the integral. So we've gotten two approximations using right-hand sum and left-hand sum. If we want to get better approximations, we can increase n. So as an example, let's just look at a few values. So if n is equal to 10, we get 0.285 for the left-hand sum, 0.385 for the right-hand sum. N is equal to 100, we get 0.328 and 0.338. N is equal to 1,000, we'll get 0.3328 and 0.3338. And lastly, when n is equal to 10,000, we get 0.33328, 0.33338. So we could keep going, but we know that the left-hand sum is always an underestimate, the right-hand sum is always an overestimate. So that means that the actual value of this integral has to be bigger than 0.33328 and smaller than 0.33338. So that doesn't leave a lot of range for this value of this integral, so that's probably a good enough approximation for our purposes in this case, seeing as you're never going to get the exact value from this sort of thing anyway. It turns out that using methods we'll learn next class, the actual value is 1/3, which is 0.3 repeating, so we can see that we've gotten a pretty good estimate of the value of this integral using left-hand sums and right-hand sums. Okay, but we can do better than this, actually. So we can use the midpoint sum instead. So let's discuss how that works. So the idea is the following. When we divide up the x-axis into these subregions, if I pick, let's say, a point here and draw my rectangle, then this rectangle underestimates the actual area on this subinterval because there's all this region up here that gets left out. If I were to draw the right-hand rectangle, then there's a pretty big overestimate because there's a lot of area in this little corner in the top left that is included in the red rectangle that should not be included in the area underneath the curve. So the idea of the midpoint rule, if I sort of redraw just that small region there, is that instead of taking the height of the rectangle to be the function value on the left side or the function value on the right side, I choose the height of my rectangle to be the value in the middle of this interval. So at some point here, which I'll call xk mid. And so I think it's clear from the picture why we might hope that this gives us a better approximation. So on part of the interval, I in top left corner some region which is being included that shouldn't be. But then in the second half of the interval, I'm actually underestimating because there's this area up here that is not included. And so that means that there's some overestimation, some underestimation. These two effects somewhat will cancel out, and overall we'll get closer to the actual area that we wanted. So for this reason, we can expect that the midpoint rule will often give better results than the left-hand sum or the right-hand sum. So let's take a look at how the midpoint rule will work. So for the midpoint approximation, we'll have f of x. Okay, so our Riemann sum will look like sum from k equals 0 to n minus 1, f of x k mid delta x. So it's very similar to what we had for our Riemann sums before, except now, instead of having the value of the height of my rectangle, this f of xk, instead of being the left-hand endpoint, just xk, or the right-hand endpoint, which would be xk plus 1, we're instead using some other point. And how do we find the midpoint? Well, it's just xk minus 1 plus xk. I think I want plus 1 actually, right? Yes, xk divided by 2. Right, so for example, when k is equal to 0, this would be x0 plus x1 divided by 2. So it's the average of x0 and x1, which gives us the midpoint of those two. So the picture is that we have x0, x1, x2, x3, and so on. And our midpoints, this formula, will give us, this would be x0 mid, this would be x1 mid, this would be x2 mid, x3 mid, and so on. Okay, so you can do a similar procedure to what we've discussed already and use the midpoint rule to estimate Riemann sums and integrals, but, or sorry, I should rephrase what I just said. You can use the midpoint rule to form a Riemann sum, which approximate the integral. And then if you take the number of rectangles to infinity, then just like the left-hand and right-hand sums, the midpoint rule will approach the true value of the area that you want to find. But it turns out that for basically all the functions we're going to look at in this class, it doesn't matter whether we use the left-hand sum, right-hand sum, or midpoint, because as n goes to infinity, they all give us the true value of the integral. So yes, if we have a small number of rectangles, like 100 or 1,000, then probably in most cases midpoint will do better than either left-hand sum or right-hand sum. But since we're mostly interested in the true value of the integral, so the limit as n goes to infinity, it doesn't matter since they all give you the same value. Okay, so I hope this gives you a bit more understanding of how these Riemann sums work and how to set them up. And in the next lecture, we'll see how can we actually compute definite integrals. Because even if we can calculate really well these Riemann sums using a computer, we still are not able to get this exact value of 1/3. No matter how many rectangles we shove into the calculation on the computer, we're just going to get something really close to 1/3, and we wouldn't know for sure that that's actually the exact value. So in the next lecture, we'll see a remarkable result which allows us to say with certainty what the value of the integral is.